I just can't wait until the second part of this talk, so let's get going.
Okay, so, all right, thanks for sticking around, a vote of confidence. All right, so don't leave after the first slide, okay? That will be the only kind of fancy word slide. So, all right, so let G be a self-adjoint group, okay? So therefore reductive. So JM is happy, now we can go on. So what do I mean by this? What do I mean by this is that, okay, it's a risky close, so the group is just captured by zero sets of some polynomial equations, okay? And if G is an element of the group, then the conjugate transpose is also in the group, okay? Like some of you like this to be a star, I like it to be a dagger, so, okay? I hope that's not contentious here, but, okay, that's the only thing. So what are examples? Okay, you know all of those, right? Like set of all invertible matrices is one of them. That's good, right? Set of all determinant matrices with determinant 1. Set of all diagonal determinant 1 matrices, and you're like, okay, that was familiar, right? We've seen that before. And products of those, okay? So that's it. So just think of like, and today I just want you to actually just think about GLN, okay? Okay, now G acts linearly on a complex vector space V via some representation. It's just a presentation going to be a map that, like a polynomial map that maps like elements of the group to like these larger matrices, right? So you can think of G here as being smaller matrices, and you map it to like a bigger space, okay? Okay, examples. Let's go to the examples. It's a group homomorphism, exactly. So now Peter is also happy. Great. So, and the example I wanted to have in mind for the whole talk, which is the example that I'm going to work on, is something you guys, everyone loves, right? Conjugation. So my group is just GLN. My vector space is the space of all complex n by n matrices, okay? And my action is just like multiply A by G inverse. That's it. Sounds good? Yeah? What are other examples, right? Like Gauss elimination, which I put in quotation marks because after the lectures this week, right, there's not just one. There's lots of things you put before, lots of quantification of Gauss elimination. So, but here what I wanted to say is like, okay, these are elementary row operations, elementary column operations, okay? And I'm just going to act like, okay, I do elementary row operations, elementary column operations. Those are going to be my actions, right? So this is also like fits into this kind of overview of invariant theory. And well, the familiar matrix scaling, right? So what's matrix scaling? Like I have two diagonal matrices of determinant 1, and I'm acting on the space of all matrices by what? Well, row scaling and column scaling, right? So you can see that kind of this general umbrella fits all of those actions that we're talking about. But today, seriously, just think about conjugation, okay? We're going to see some cool things happening there.
Sorry, can we go through it one more?
Yeah, of course. GLN here is the dimension of this V here, right? So,
okay.
Yeah, when I say GLN here is just saying like this is all the invertible matrices, like n by n invertible matrices, right?
Okay.
So if the dimension of V, when I say GLV, if the dimension of V is n, right, you can replace this by GLN.
I see, okay.
Yeah?
Okay. And then the group is like I'm thinking as the action, like in the group I have, for example, the diagonal scale.
Yeah. Yeah.
But then I'm applying that to some object that's not.
That's a vector. That's in the vector space, right? Like A is a matrix in my vector space.
Okay.
Right? And how does the group is acting on the vector space? Is like, okay, I multiply on the left by diagonal, I multiply on the right? So I'm still in the same vector space. This is still a matrix, right?
Okay.
But it's a different element.
Yeah, I see. Okay.
Does that make sense? So I'm moving it around. Right, so yeah, it's the same kind of thing as in the last lecture, like, okay, I had a matrix A, and I want to like scale it to double stochastic. Then what do? Well, my only operations that I wanted to do is just to scale, right, x1 up to xn, y1 up to yn, and this takes A to a different matrix B, right? And that's the action, right? So I'm just writing this as like, this is the action of this guy that I'm going to call G, and this guy that I'm going to call H. This is pi of GH. Does that make sense?
Acting on A.
Yeah, acting on A, sorry. Acting on A.
Okay.
Right, is the action of the group. Right? Or you can think of the group acting just by conjugation, right? If I have A, which is a matrix, and the only action that I'm allowing you to do now is to conjugate that matrix, what do? You're going to just like multiply on the left by G and multiply on the right by G inverse. And that's a different matrix, right? But it's related to A because it's a conjugate of A.
Okay.
Does that make sense?
Yeah.
Great. That's great. Yeah, I want to go very slow now. So ask all questions all the time.
Similarity transform a bit.
Yeah, great. Sounds good? Okay, so we have these examples. And, okay, but once I had these examples, like, once I had this group action, then there's these geometric objects that naturally appear, right? So what are these geometric objects? Well, this is the orbit of an element of my vector space, which is what? Well, take all possible actions like of the group on V and take that set. That gives me an orbit, right? So for example, if I take A, what's the orbit of A under conjugation? Well, it's the set of all possible conjugates of A, right? The set of all of these elements, like for all G in my group GLN, this is my orbit. This is what I'm saying, like this is my orbit of G acting on A. Does that make sense? So it's all the other matrices that are similar to A. That's an orbit. Yeah? Sounds good? Okay, but remember, just the same way that we were talking about matrix scaling, that there was those matrices like morally scalable, right? There are some things that are like very close to the orbit, but are not in the orbit. Right? For example, if you take a non-diagonalizable matrix, right? Like, and then you try to diagonalize, well, you're going to get very close, but you're never going to really get to the diagonalizable because the matrix was not diagonalizable. But you get very close, which means that we're just going to add the closure to it, and we get the orbit closure. So it's the orbit plus all its limit points, okay? And limit points, you can think of Euclidean geometry. I'm not going to, a lot of details for the experts. The talk is, I was told that this talk is not for you. So, but you know what I mean. And if you don't, I hope that this makes sense to you, right? So I'm adding all the limit points. Sounds good? You're an expert. I'm kidding.
You could take a Jordan matrix, which was there all the time during this week. So, and then when you just act with the group, you cannot get the zero matrix. But as a limit, you can. That's an
Exactly.
example. The limit point you add would be the zero matrix. That's something really very concrete.
Yeah, and we're going to see that.
Then you specialize it.
Right, and we're going to see that soon. Like the main example I'm going to work on is just the conjugation for today, right? Okay, so here's problems of interest, okay? And we saw one already from matrix scaling, right? So if I give you an element of my vector space, like remember the matrix, right? Is 0 in the orbit closure, which means like can I act with the group and get as close to 0 as I want, right? That was like part of the matrix scaling problem, right? The other version. So this is just generally called null-con problem. So, I mean, if you want to say, like, Hilbert was already working on matrix scaling, right? So, and then the other one is, well, suppose that I have, like, 2 points, and they define 2 orbits, and therefore 2 orbit closures. Do they intersect? That's a natural question. The other one is, well, if I have 2 vectors, again, they determine their orbit. Is one orbit contained in the other? Right? And the other one is, well, I won't talk about this today, but you can ask me, or Akshay, or Michael Walter, or Peter. They're much better than me. So, okay, which is the moment polytope. So it turns out that related to these orbit closures, there's a polytope, like an honest polytope associated to it. Okay? And then the question becomes kind of your usual question. I have a vector v. Its orbit closure defines some polytope, which is called the moment polytope. And now I have a point, like a real point. Is P inside of this polytope? Right? It's a membership question. Yeah?
So when we talk about limits, these are objects in this vector space V. Are we just using an ordinary norm topology, or is it something funny?
Very good. We're going to talk about the norm in a second. Yes. And there's always...
Yes, the usual.
Yeah, is the usual norm is, and I'll tell you what usual means here in a second. Huh? P is P in this moment polytope. Sorry, like even the vector V, its orbit closure defines this polytope that I call delta V. And what I'm saying is that this P does not live in the same, like, it doesn't live in the vector space. So P lives in some other space. Yeah, this polytope is in some other space. Right? And then I'm just asking if P is in this polytope. Right? But I can give more details later, but I'm specifically, like today, I'm just going to talk about the null-con and orbit closure intersect, because just to define this would be, I'm here through the semester, I can explain this to you later. So, okay. All right, but once I have all these questions as a computer scientist, the first thing that you ask is like, okay, well, what is the complexity of all of these problems, right? And also, like, is it useful, right? So are there connections? Well, okay, non-con and orbit closure intersection, we're going to see it in a bit. But the things I'm not going to tell you today, I'm just going to kind of tell you a little bit about them. So orbit closure containment. So, well, it's kind of essentially, there is a P versus NP question in algebraic complexity theory. And if you put closures on these, if you look at this in this complexity like in the geometric sense, which is the focus of geometric complexity theory that JM can tell you all about it, is essentially an orbit closure containment problem. And this is the orbit closure essentially, okay, is the orbit closure of the permanent containing the orbit closure of a bigger determinant, a not so big determinant. That's roughly what this conjecture is, okay? And, well, you've been seeing border tensor rank in the other lectures, and border tensor rank is also an orbit closure containment problem, right? Because, well, if I have my tensors T, there's this group that acts on each of the pieces, right? So it's product of GLNs. And we know that the rank of this tensor is less than or equal to R, remember from the matrix multiplication, right? If and only if the orbit closure of T is contained in the orbit closure of this guy. And you might say, wait a second, no, but paying attention to the lecture, all I wanted was that T is inside of the orbit closure. But if T is inside of the orbit closure, like its whole orbit is inside as well, right? So that was the, that's the kind of main reason for the orbit closure. Does that make sense? So this is orbit closure containment, not intersection. Sounds good? And moment polytopes, where have you seen this? Well, if you want to scale to like, if you want to decide this RC scaling, if I have a matrix and I want to say like, can I scale it to like RC scaling? This is, I'm telling you, take it on faith, I can explain later. This is a moment polytope question, okay? And well, Jim mentioned Braskamp-Lieb inequalities. Well, Braskamp-Lieb inequalities are also like a moment polytope question, okay? So these are very kind of important inequalities in functional analysis. They turn out to be also, they fit into this invariant theory framework. But I won't talk about them here. Okay, questions so far? Good. Okay, so, and then again, remember, we had this scaling action and we had those like permutation polynomials that were invariant and they were quite useful for us, right? So, okay, the same way here that if a group acts on my vector space, let's just say that, let's just denote by this, like just think of this as the set of all polynomials over the vector space. So if my vector space is like, maybe I cannot write here, but if my vector space V, and I want you to just think of V as being like Cn, right? So if V is Cn, what is Cv? Well, Cv is just going to be like, you can think of it as Cx1 up to xn, right? So it's the polynomial ring. Now, once I have these polynomials, like some polynomials are special. Like when the matrix scaling action, I had those permutation polynomials, right? So they were invariant. So, okay, so my invariant polynomials are going to be the polynomial such that its value on any element V does not change if I apply like a group action here. Does that make sense? The polynomials that don't change for any V, right? Okay, and the set of invariant polynomials, they clearly form a ring, right? Because if I have two invariant polynomials and I multiply them, well, they still don't change if I act with the group. And if I add them, the same, right? Well, okay. So here are some examples, right? Let's look at the conjugation action. Well, what are some invariant polynomials? I know that the trace of x is invariant, right? I know that the trace of x squared is invariant, and so on. Right? But it turns, and you're like, oh, well, yeah, I also know that the determinant is invariant, right? But you can write the determinant like from these polynomials, right? So, and essentially you can prove that actually the set of all invariant polynomials for the conjugation action are generated as a C algebra by all of these polynomials, okay? And the proof is the same as saying, okay, if I act by permuting coordinates, is a similar proof that like the elementary symmetric polynomials or the power sum polynomials generate all the invariant, all the symmetric polynomials. And symmetric polynomials are the invariant polynomials as well. Does that make sense? Okay, so for conjugation we have, this is the ring of invariants. And if I do Gauss elimination, okay, that's great. I only have one determinant. Any other invariant has to be a polynomial of the determinant. Okay? And for matrix scaling, guess what? All the invariants can be generated by the permutation polynomial that we talked about, the permutation monomials. Okay? So this is kind of cool because before Sinkhorn, right? So Hilbert in 1893, he defined the null cone as, okay, let's take the set of vectors V whose orbit closures contain 0. Okay? So you can think of these sets as like special points, like bad points, or and what he proved in 1893, this very famous paper, right? It's like where Nustellensatz came from, right? So is that the V is in the null cone if and only if when I take any non-constant invariant, it vanishes on V. So it's an if and only if. Okay? So the null cone here is actually what we call an algebraic variety. It's the zero set of a bunch of polynomials. What polynomials? All the invariant polynomials. The non-constant ones, of course.
Why is it called a cone?
What is called a cone? Because like if this ring here, like in this action is a linear action, so like if I multiply or divide by any scalar, like I'm still.
But even negative scale is okay, right?
Yeah, that's okay. It's not a convex cone, right? Like I don't have like yeah, it's going to multiply by any complex. It's fine.
Any complex number.
Yeah, any complex number is fine. Yeah. Okay, more questions?
Maybe you can explain one implication in PVC, which is very easy.
Yeah, okay. Yeah, certainly, sure. If you ask so nicely like this, right? Like, okay, there's one direction here that is easy, right? What is the direction? Well, if 0 is in the orbit closure, then I know that all these polynomials must be 0. Why is that? Because remember, if 0 is in the orbit closure, and polynomials are continuous functions, right? So I know that I take the polynomial in V, and then this is the same as the polynomial in any action for any group element, correct? So this value doesn't change. But remember, there is a limit that converges to 0, correct? Like this guy is going to be 0, right? And if my polynomial is homogeneous here, then what happens? Well, this is going to be, essentially in the limit, this is the same as also P of 0. And if my polynomial is like homogeneous, which all of those are, as you could see, like they're always generated by homogeneous polynomials, then this is 0. So I know that if 0 is in the orbit closure, which means that if I'm in the null cone, then I know that I must vanish on all the invariants. Okay? And the other direction is the harder direction. Okay?
So you insist that the polynomials are homogeneous?
Yeah, I can because my action is linear, so they will be homogeneous anyway. You can prove that that you can generate them by homogeneous polynomials. So, okay. Sounds good so far? Great. So, all right, so let's look at examples of null cones. So now we have Hilbert's theorem. Then right away, we can see that like geometrically, just by thinking of in this geometric perspective, we already see, oh, the conjugation action, the null cone is the set of all nilpotent matrices. Right? Because the nilpotent are the ones that, like, if I take the trace, like all my eigenvalues are 0, which means that the trace of all my powers are going to be 0. Right? So right away we get, oh, okay, the null cone, it's a cool set, right? It's an interesting set. It's a set of all nilpotent matrices. And for Gauss elimination, remember, I only had one polynomial that generated every one, which is the determinant. So my null cone here is going to be the set of singular matrices, right? And matrix scaling was those guys that cannot be scaled to doubly stochastic, right? So does that make sense? So these are some examples that are like, oh, the null cone is capturing something interesting. Okay, now let's talk a little bit about orbit closure intersection. Like there's something, you can milk more out of this like theorem, right? Which is known as the Hilbert-Mumford theorem, which like these invariant polynomials, they can also capture if two orbits intersect. Orbit closures intersect. And what's the theorem they're saying? The Hilbert-Mumford theorem that says that these two orbit closures intersect if and only if their values on all the invariant polynomials are the same. Right? Which makes sense again, and there's an easy direction, right? Like if the orbit closures intersect, right, I can do the same reasoning here, and I can say, well, take P of V and take P of U. Right? Well, the orbit closures intersect, which means that I can kind of scale U and scale V towards the same guy, which means that this guy will be the same as the value of the element in the orbit closures. Does that make sense? So one direction is easy, the other direction again is hard, but you can prove it. Right? And here, what do we get from the Hilbert-Mumford theorem? For example, orbit closure intersection captures what? Well, Conjugation problem, conjugation action, what is it capturing? Well, if two matrices have the same set of eigenvalues, okay? So that's if and only if, like, so two orbit closures intersect if and only if two matrices have the same set of eigenvalues. And why is that? Because again, right, like, if I take two matrices A and B, right, their orbit closures intersect if and only if, well, these guys are equal to all of the invariants. But remember, the invariants for the conjugation action, they're generated by who? By the trace of powers. Which means that A and B will intersect, like the orbits intersect if the trace of A k is equal to the trace of B k for all k. But what is this? Like this is the sum of the eigenvalues of A, sum eigenvalues of B to the k. But this can only be equal for all k's if the eigenvalues are the same, right? So, okay. So you see, like orbit closure intersection, we already get, okay, conjugation action, like this Hilbert-Mumford theorem already shows, okay, is if and only if two matrices have the same set of eigenvalues, right? And for Gauss elimination, well, it's only if both matrices are invertible or both of them are singular.
I got confused about, I thought you said the invariant polynomial for that one was the determinant.
For the Gauss elimination one, yeah. So,
Because they're both invertible doesn't mean they have the same determinant, or I think I missed.
oh, yeah, no, sorry, yeah, they have the same determinant. Sorry, I have to say the determinant.
Oh, with the same.
Yeah, because, sorry, that is my typo here, yeah. I was acting with, I'm acting with SLN, so I'm not changing the determinant. Yeah, thank you. Thank you for catching that, yeah. They have to have the same determinant. Yes. Okay, more questions? Yeah.
Do you require the eigenvalues to have the same multiplicity for that, or?
Yeah, it's the same with multiplicities, exactly, yeah. Okay. So,
Actually,
Yeah.
if you include permutations in Gauss elimination, wouldn't it be the determinants are the same up to sign?
well, you have permutations, right? Because I have SLN, so all the yeah. So, oh no, yeah, but I have determinant. Yeah, okay, up to sign. Thank you. I forgot because yeah, some of them have determinant -1. My bad. Yes, thank you. Two typos here. I'll fix this later, guys. Yeah, Gauss elimination. I knew I would have trouble with this here, in this crowd. Okay, right? But the null cone is not just like it's not just well, the null cone here, we can see the null cone through the lens of like optimization, right? Because here, what am I doing? Well, I have all the vectors. What's the vector of smallest norm among all the vectors? 0, right? So when you're saying is 0 in the orbit closure, right? It means what? Well, this problem is related to this problem here, which I'm going to call capacity, right? So the capacity of a vector is just going to be the minimum norm, the element of minimum norm in my orbit closure, right? That's what this infimum means. Right, which norm? This one here. Yeah, I knew this was going to be asked. Right? So it turns out that every time a group is acting on a vector space, there is a preferred norm that you should use, right? Which is the G unitarily invariant norm on V. And what does that mean? It means that like when I act by unitaries, my norm should not change, right? But now I'm mapping like small matrices into like a bigger space of matrices, right? So it turns out like which norm do I pick? I want to pick the norm that if I use a unitary from my group G, it will go to a unitary in the other group. So that's the norm that I will pick. So there's always a norm that you can pick, which is the unitarily invariant norm. Yes, that's correct. I'm going to pick one and be happy with it. Yeah. So, okay, so the capacity here, again, this will disappear in the next slide, so just work. And whatever norm you use, for example, conjugation, it will be the Frobenius norm. Okay? Let's just stick to that one.
Is that non-unique?
Huh?
Is that non-unique?
It's unique
Up to-
G is irreducible, but if G is a product, then
Yeah,
as many factors as the product.
correct. So, all right. And then here, again, so now we know that V is in the null cone if and only if my capacity is 0, right? Because the minimum norm here will be like 0, the infimum norm. Does that make sense? Okay, so now we're going to see this in terms of optimization. But if you remember, I can define as well, like, because separating 0 from non-zero is a little bit bad, I want to zoom in on the closing to 0, right? Or close to 0. And I'll zoom in by putting a log here. So if I'm going to minimize now the log of the norm, I get the log capacity, right? If you remember, and if I do like, okay, I'm going to call this function here my log norm function. And if you remember, well, this is also known in the literature as Kempf-Ness function, okay? And if you remember, this is exactly the same setting that we had in the matrix scaling problem, right? We wanted to minimize a norm, and I said, oh, actually, but log norm is good because I'm doing like minus infinity to finite, right? And then I had this function here, correct? That was exactly the log norm function, the matrix scaling problem. Okay, great. So, okay. All right, so now here's our problem, which generalizes that one version of matrix scaling, right, which is the norm minimization problem. So I'm getting an element v from my vector space. I'm getting epsilon. And I want to decide whether my capacity is 0, right, whether I'm in the null cone or not. But if I'm not 0, I want to find like an element of the group such that the norm of this guy here is epsilon close to the minimum log norm, right? Does that make sense? Okay, so this is our first problem. And again, when G is a Lie group here, well, the Kempf-Ness function is actually geodesically convex. So it's convex, but we need to talk about a different geometry, right? The same way that when we talked about matrix scaling, I just switched my parametrization, right? So I'm going to do the same here. So it turns out that this function here is convex in the Riemannian geometry defined by my group G. Okay, so please don't leave the room yet. We're just going to do a simple example. So the main example of the geometry that we're going to talk about here is something that's very familiar and all of you like know and love, which is positive definite matrices, right? And why is that? Because if I take my function here is the log norm, which is half of the log norm squared. But now the norm squared is the log of the inner product. But if I have the inner product, like this guy becomes the adjoint here. And then if I have like the adjoint like times my matrix, this is a positive definite matrix, okay? So let me just give you again, let's go back to our conjugation action, like our simple example. Well, here's like my norm, here's the Frobenius norm. So I'm going to do this log norm is half of the log of the Frobenius norm squared. But the Frobenius norm squared is what, right? Is the trace of A star A, so, or A dagger A, right? But what is that? It's going to be like log, so it's going to be half of log of the trace of, well, but I have to do this A star A, right? So it's going to be G A G inverse star G A G inverse, correct? And now what do I do here? Well, when I change this, so now I'm going to have like G minus dagger, A dagger G, dagger, G, A, G inverse, correct? But the trace is cyclic, right? So I'm going to send this guy here. My trace doesn't change, right? And I get exactly what I have here, but I kind of messed up the P here. So this should be P, and this should be P inverse. So the minus ones are changed here, right? But remember, P is just an invertible matrix conjugate transpose times the same matrix, right? So this is always positive definite, right? So does that make sense? So now, oh, I cycled again, right? Oh yeah, yeah. Oh yeah, because this is P. Oh yeah, P. A. Okay, thanks. Great. Yes, I cycled everything again. All right. Oh, sorry. Yeah.
Maybe I can also give some intuition. So if Rafael said that the norm we picked was unitarily invariant, so the function doesn't depend on the unitary.
Right.
So we may as well mod out by the unitary, and what we're left with is.
Right. That's just a different like diffeomorphism, right? It's like the one, or yeah.
Like
So do you assume that G is a unitary matrices because otherwise you are in trouble?
No, I'm not in trouble. I want G to not be unitary because if it's unitary, the norm doesn't change.
Okay, but then of course Frobenius norm is not invariant under G2.
No, he said the unitarily, that you take a unitary subgroup of G.
Yeah, then it's fine.
But that's what he said.
Okay,
You gotta pay attention.
so the norm is for the your invariant norm is for the unitary matrices, right? Frobenius norm.
Yeah.
But so it's not invariant under the general group.
Maybe I hope whether it helps, but for the experts, actually, we don't put this Riemannian metric on the group, like think
Right.
of GL, we mod out by unitary group. So there are two options, left or right cosets,
Right.
to figure out which one. And this homogeneous space is then the manifold.
Yeah.
That's the right way of seeing it. It can be overwhelmed.
Right. All right, so back to the non-experts, right? So, okay. So here, like now, if I have this Riemannian manifold, like, which is just the manifold of positive definite matrices, right? So what is my geometry there? How do I go from one point to the other, right? I go via the exponential map, which in this case, the exponential map is very easy. So if I start at a point P, and my tangent direction is the set of all like Hermitian matrices, okay, for this space. So how do I go from P to anywhere else? Like from P in the direction H, I just take P half, exponential of TH, and P half. So this is going to be my curve. So these are going to be my geodesics. Okay, so all my geodesics are like this. From P going to the direction H is a Hermitian matrix, is just going to be this curve. And you can see that all of these are like positive definite matrices, so, right? So, okay. And let's just stick to this, right? So now, what do I want to say? Well, here's the thing. So now that I have like a convex function, right, the geodesically convex, I'm going to keep dropping this geodesically convex because you know now that it's convex along those geodesics, right? So we can compute the gradient. And this gradient is what's called like the moment map. So, but I'm just going to refer to it as, I'm going to use this notation because it's simple, but all I'm saying is that is the gradient of my function. And I can also try to minimize the norm of the gradient because remember, if I have a convex function, minimizing the function or the norm of the gradient is the same thing, right? So it's the same thing that we did for matrix scaling. But you can see that it fits already in this very general setting. Like I don't need anything else besides this information. And okay, so what is a cool fact here? So what is my, when I'm doing the conjugation action here, right? What is my gradient? So let's compute the gradient here. And you see that the gradient is essentially like how far my matrix is from being like normal, which is kind of cool, right? At least I think. So what's my gradient? Well, my gradient here on the group A, I'm going to drop G, right, like of A, and I'm just going to get the gradient of A at the identity. So, well, if I go in the direction H, which is a Hermitian matrix, this is going to be what? This is going to be my derivative evaluated at 0 of, well, there's going to be a half here, and I'm going to have log of my trace. And here I'm going to have my P. Remember, there's a 2 there that I forgot to put here, but it's OK. Well, but my P here, my P is at the identity, so I'm going to have like e to the 2 th, a e to the minus 2 th, a conjugate transpose. Okay, that's my direction, right? Because I started the identity, and then I'm going the direction e. So P, if you remember this P half, that should be a 2 here, but this P half is just identity. So it's identity, identity. So I'm just going on this direction, right? And when I take the derivative, what happens here? Well, the derivative of the log is 1 over this. When I evaluated this at 0, what do I get? I get exactly just the trace of a star, which is the norm squared. Oops, sorry, which is the norm squared. So I'm going to get half norm squared of A, which is the Frobenius norm here. And then I have to do what? Well, I have to take the derivative of this guy, right? But what's the derivative of this guy? Well, I can just write the exponential here in its Taylor expansion. And all I need to do here is in this whole expression, I need to pick out the coefficient of t, right? Because that's going to be my derivative. But what's the coefficient of t? It has to be th times a. I need to pick the identity here. So it's going to be a star, right? And now, if I want to pick this coefficient of h here, it's going to be what? I have to pick the identity here, so it's going to be plus identity times a.
Plus or minus?
Yeah, but I'm going to pick the coefficient here, so it's going to be minus 2h.
Okay.
Yeah, yeah, it's fine.
And then,
A dagger, right?
and you need the 2 in the first one also.
Oh yeah, the 2 is my bad. Yeah, so t, yes, 2h, thank you. Right? So, and I have the trace. Right? Does that make sense? And now, well, what is this here? So it's going to be the trace of this, and then I'm going to have to I take the derivative, the t disappears, and when I set it 0, this is my constant term. Right? So it's going to be exactly like the trace of, well, the 2 cancels, so there's a 2 here and a 2 here. It cancels out with this 2, so I'm going to remove this 2 here. And then I have h times a dagger minus a. Well, but trace is cyclic, right? So I'm just going to replace this a dagger here. So I'm going to do a dagger a times h. Correct? But the trace is cyclic, so I can replace this guy as well by a dagger h minus this. Right? So if I see the inner product, well, my gradient has to be what? Everything that's multiplying by h. Right? But this is exactly the inner product of like a dagger minus a dagger a over the norm of a squared h. So this is my gradient. Does that make sense? So that's very simple to compute gradient. That's why I wanted to compute here to show, like, don't get scared about this. Like, you just kind of, you can do this. We can all do this, right? So, and the conjugation here is saying, well, okay, this is how far I am from being normal. A goal that we should always try to achieve, right? Being normal. So, okay. But the thing is, okay, but this is kind of cool because it's saying what? Well, if I'm minimizing the norm, I'm also minimizing my distance from being normal, which means that, like, right, when I go and I'm optimizing, like when I'm minimizing the norm, this optimization problem is telling what? Is driving you to the normal matrix that is similar to you. This is also pretty cool, right? Very inefficient way, of course. We saw many algorithms or whatever. I'm not talking about efficiency. I'm just going to talk about cool things, right? Well, efficiency is also cool, but yeah.
What's the intuition behind monitoring the gradient identity?
Ah.
What makes it work out?
Yeah. So essentially the same. The reason is because there's this notion of equivariance. So it's saying like the same. Sorry, can you repeat the question now? I know. I'm asking him to repeat so I can repeat. Because I want to repeat exactly what he said.
I get that taking the derivative at the identity made this all work out, but what was the intuition behind why we're taking the derivative at the identity? Why do we care about the derivative at the identity?
Exactly. So the question is, why do I want to compute the gradient only at the identity? Why not compute the gradient everywhere? It's because there's a trick that to compute the gradient everywhere, you first move to that point, and then you compute the gradient at the identity there, at that point. So these functions satisfy this property, which is called G-equivariance, but I don't want to use the name. But essentially, these are like the gradient of A at any other point is the same thing as going to the other point, looking at this function f of b, and computing the gradient of f of b at the identity, which is the same calculation that I did, but I just replaced a by b. So that's a trick. That's a trick that, okay, it's a property of these functions. Okay? So that's why I only compute gradients at the identity. So it makes our life much easier. Does that make sense? Cool. So, okay. So now, again, remember, so now we found like our function is convex, so minimizing the function is the same as minimizing the gradient. So now we get the equivalent problem, which is the scaling problem. Right? Like, so again, I have a V in my vector space. I have epsilon. I want to decide whether capacity is 0 or not. If it's not 0, then I want to find a G that minimizes my gradient. That was exactly the matrix scaling problem, the first version. Right? It just happens that here it comes as the second version. That's the only difference. Okay? And, okay, so Kempf and Ness proves that, okay, that this function is geodesically convex, and therefore it's the result that, okay, the capacity is bigger than 0 if and only if this infimum here is equal to 0. Right? That just follows from the convexity in this Riemannian manifold. Okay? And again, so what did we get? We get that in this very general setting, this norm minimization problem that we talked about and the scaling problem here, they're dual problems. And that's what we refer to like as non-commutative duality. So every time you hear us talking about this is exactly what we're talking about. Okay? And okay, well, in this book that we're writing, so, well, we prove a quantitative version of this. Okay? So, which is a relation by how like the gradient is, the norm is to like the minimizer and the gradient. So, and then we also give first and second order algorithms for these problems. Okay, in this very general setting. which would say the same thing. Like, so this, if you specialize this to like the matrix scaling setting, you get like the first and second order algorithms for these problems there. But again, those ideas that you saw in the first lecture, they can be generalized to this setting, okay? It's not that bad. It just involves like, okay, now you need to control the parameters like to analyze these algorithms, and these parameters are coming from the representation theory of this action, okay?
So for when your group is like the similarity transforms, does this lead to some notion of an eigenvalue algorithm that we might be familiar with? Or? Like, I guess you could run your algorithms to move a matrix to a normal matrix.
Right.
And then compute the eigenvalues of that normal matrix, and this would be a algorithm for
Correct. That gives you an algorithm, right? Because the limit here, you're going to get like the minimum norm is exactly just the diagonal matrix. So it's going to be your eigenvalues. But again, you know a lot more algorithms on this than I do, so I don't know if this corresponds to one that you know.
Maybe I have a question, actually a question I wanted to ask people in the medical analysis here. There are, we make this quantitative, and there are at least two measures of how close you are to being a normal matrix. So one is this A dagger minus A dagger norm, how small. And the other is expressed in terms of, I have to figure out not to mix up the singular values with the eigenvalues. So like a primal and dual conditions, and one get inequalities, which I think are interesting, but I haven't seen it anywhere. Maybe that it is new, but I'd like to ask. You're here in the semester.
I don't know actually, but
maybe
Nikhil might
somebody
know more,
else.
yeah,
Maybe
like-
Mark,
Mark, yeah.
This is. There may be something new coming out here, even in this space.
We can talk to them later, yeah.
Maybe I can give a
Okay.
suggestion. There's a lovely theorem called Lin's theorem, which
Sorry, which theorem?
Lin's theorem, which bounds the distance to normal by this quantity actually.
The distance norm meaning like like for Venus norm difference.
Yeah, exactly.
There's a Jacobi-based algorithm by Axel Rua for computing normal matrix, but I don't know that that's been used very effectively. It has a great paper title, Nearest Normal Matrix Finally Found.
All right, great. Okay, we can talk more about it. Okay, great. Okay, I did not know about this either, so all right, awesome. So, okay, more questions, comments, algorithms? Okay, so, all right, and now, like, I won't give many details, right, but I just want to conclude here a little bit with, like, okay, let me just give you another group action. So we've seen a couple of group actions, and we saw, okay, optimizing this, we're finding, like, a normal matrix, and the minimum norm is going to be your diagonal matrix, right? So this is cool that you can find, there's an optimization formulation of, like, conjugation. Like how do you diagonalize, right? Like approximate diagonalizable. You can see this is a convex optimization. And in 2004, like Gurvitz was studying this following action, like which he called like operator scaling because it has to do with like quantum operators. So, but I won't talk much about that here. But essentially the action is going to be like I have two SLNs, so two matrices with determinant 1, and they're going to act on a tuple of matrices. Okay, and if you know a little bit about quantum information, these are going to be like the Krauss operators of your the Krauss representation, like the Krauss operators of your quantum channel. And the way that you move from one channel to the other is just by simultaneous left-right multiplication. So you're going to multiply all of the matrices on the left by the same matrix and on the right by the same matrix. So that's your group action. Right? And what it turns out is, okay, what is this action good for, right? So matrix scaling had a really long list of cool applications. And what it turns out is that operator scaling also has a ton of really cool, is related to a lot of cool problems. So for example, is related to the instability of quivers. Well, Akshay, who's here, like one of the experts, used this, and collaborators, they use this to solve the Paulson problem. If you care about non-commutative algebra, this is also used to compute like the non-commutative rank of a matrix with non-commutative entries. Okay, you can do even more Sylvester-Galite things. Again, well, now you can actually deal with the original Schrödinger static bridge problem in quantum. Okay, back from 1931. So this is work of Cole Franks, and also Cole did like solve the like an algorithmic solution to the Schur-Horn problem. We can use this action here. So Braskamp-Lieb is related to this action here. Okay, it's moment polytopes for this particular action. And recently we also used this action to give better sample complexity bounds, like nearly tight sample complexity bounds for the matrix normal model. Okay, this was open until recently, and we use this this geometric, like this optimization perspective to give a very nice proof of sample complexity bounds for the matrix normal model.
When you say short-form problem, is that the same thing that gets called one problem, or is this a different one?
They're different. Yeah, it's like the three matrices, and I have like the sorted eigenvalues, and I want to say, okay, when can I realize like three Hermitian matrices?
Yeah,
That's the Horn problem. Yeah. Okay. So, and if you want to know more about this, okay, so there is a survey on matrix scaling and a little bit of operator scaling by Edel. There's another survey on operator scaling by Ankit and I. And then again, we have this book that's coming out, and I want to advertise this, right? So please, like, yeah, our book is going to be cool and it's going to be accessible. We're working hard to make it accessible to everyone.
And you've decided on a year.
Huh?
And you've decided on a year.
Who's very optimistic.
Yeah.
Especially
So.
with 6 authors.
It's a great acronym.
It's a high communication complexity.
Yeah.
You should minimize communication and it's not fast to solve your problem.
Right. Yeah, maybe I should put a plus here, but I'm hoping it'll be this year. So
So you guys have a draft online?
we have a draft. It is online, but not for you. It's online for us. It's an overleaf, so it's online.
She's moved.
Yeah. So, yeah. Okay, but now I want to conclude like this kind of survey on scaling problems with some open questions. Like, what is open? Like, there's lots of things open. So, and one thing I wanted to comment is that I didn't touch much on like the invariant polynomials, right? I just stated those polynomials in the beginning, but I didn't say much about them, right? So how are they helpful? So, okay, so there's this there's this algebraic geometric approach, right, that I just hinted at with the Hilbert and Hilbert-Mumford. And then there's these variational approaches, right, these optimization problems and convex duality. Okay, so, and I talked a lot about the optimization one, but here's the thing. So can we understand better like the algebraic and these approaches, both of them? Both of them need a lot more understanding. There's a lot of questions that are open about them. So for example, for many of the above problems that I talked about, for example, if you want to decide if a matrix can be scaled to double stochastic, can you do that algebraically? And the answer is yes. Okay, there's a very simple algorithm. And because it's the same thing as to say, look at the bipartite graph of the support of the matrix, and you want to decide if that has a perfect matching, right? And how do you do that? Well, it turns out that Edmonds, back in the day, 1956, and even Tutt actually did it before Edmonds and in a more general way, but I won't talk about that. I don't want to be contentious again. How can you do that? Well, let me look at my matrix A. And again, if you remember, if I look at the support of A, I'm going to get like a adjacency matrix here, right, from the support of A. Correct? And I want to know, like, this is going to be an adjacency matrix of some graph. And this matrix is scalable to double stochastic, approximately scalable to double stochastic, if and only if this guy has a perfect matching, correct? How can I do that in an algebraic way? Here's how I can do it. So here's the idea of Edmonds. Let's say that this matrix here is the matrix Aij. Then what Edmonds said is like, well, Shmuel was saying, okay, I can look at the determinant of this matrix, right? But the thing is that if I look at the matrix like this matrix, is the complete graph, has a perfect matching. Determinant is 0. So it doesn't work for this guy. However, if I replace the entries from being 1 to being just distinct variables. So here's the matrix I'm going to construct. It's the matrix xg, which is going to be a new variable, a fresh variable xij, if aij is different from 0, and 0 otherwise. Then my matrix has a perfect matching. Like this graph G has a perfect matching. So G has a perfect matching if and only if the determinant of xg is different from 0 as a polynomial, right? And why should you expect this? Well, it's because the determinant, remember, is a function of all those permutation monomials that we talked about. So this is an invariant that combines all the other invariants very, like, in a smart way, right? But how do you test that this is different from 0? Well, just evaluate at a random point, and then you can do your Gauss elimination. You can do whatever algorithm you want on it, right? And like, wait a second, but what kind of numbers can I plug in here? You can plug like all the numbers between like 1 and 5, and you get your algorithm succeeds with probability 80%. Does that make sense? So this is an algebraic algorithm, right, that decides already whether I'm scalable or not. Now, of course, algebraic methods, there's questions like they cannot solve an optimization problem. They can just give you like some answer, like can I do it or can I not, right? But still, there are many problems that the algebraic approach is also good. So can we better understand those? And it turns out that like for matrix scaling, well, Edmonds had this theorem, right? And for the operator scaling, like Harm, Dirksen will be here. So for many of these questions that can be answered by the algebraic methods, we also have simple and efficient algebraic algorithms. So Harm is going to be here. Yu Ming is also going to be here. So they both did a bunch of these like algebraic algorithms. Yeah.
Based on the title of the workshop that is coming down the road, do you guys care that this is a randomized algorithm, this algebraic?
I particularly don't care.
Okay.
Well, I care. Well, it depends on the setting. For some settings, I care because I would like to de-randomize a couple of problems, right? So for example, for the perfect matching, like we know, like can we de-randomize this algorithm? Like can we make it parallel? Because this is a very fast parallel algorithm because you can compute the determinant fast in parallel by algebraic computations, right? So parallelize like so. This is this is the simplest parallel algorithm for perfect matching, right? And we don't have another like just non-randomized, like deterministic parallel algorithm for perfect match. That's an outstanding open question, right? So in some settings you care about the randomizing. The other questions, there's many other questions that are much harder that we just want any algorithm, whatever we can get. So, but definitely, yeah.
But maybe you could mention that it has, this operator scaling has led to this amazing progress where you are part of about polynomial identity testing and setting. You didn't even say.
No, I say it's here, but I didn't say much. Yeah, I don't want to brag about it.
One item among many, but
yeah.
But there it's exactly about the de-randomization. So this approach
right.
helped to prove in the setting of non-commutative polynomials or rational functions that we de-randomize polynomial identity test and polynomial determinism. That's proven by this method.
So yeah, and actually, not only that, but it was also like, so this problem also was originally also, one of the motivations that Leonid had was that Leonid wanted to de-randomize PIT. For those of you who know, like I mean, maybe like, he wanted to de-randomize it via optimization. It was a really cool idea. Like, and it turns out that actually this problem, this operator scaling problem that he came up with, doesn't solve the commutative polynomial identity testing, but as Peter is saying, it solves a non-commutative version of it, which is the rational identity testing. Okay? So yes, we want, like for example, the cool thing about optimization is that for many algorithms, these are deterministic, and we can get de-randomization of certain problems. But for certain problems, we even want just efficient randomized algorithms. So for example, moment polytope, like a lot of people care about it, like physicists care about it, chemists care about it, and if you give any efficient like randomized algorithm, that's good for them. Yeah.
So for there is a polynomial identity testing problem here. It's like I give you a sparsity pattern of a matrix, then I say, is the polynomial, which is the determinant, when those are viewed as, those non-zeros are viewed as variables, is that identical to 0?
Exactly.
And I guess, we saw, I guess, a deterministic algorithm for doing that. You know, the Sinkhorn stuff? Right?
Exactly. So Sinkhorn is the simplest like algorithm to decide if a graph has a perfect matching or not, right? Just pick the adjacency matrix and scale it. 3 lines of code, that's it. Like that's the simplest algorithm for deciding if a bipartite graph has a perfect match. That's correct, right? So that's one way in which, but that algorithm is sequential, right? Like all these algorithms, you're optimizing, you can only prove like you're gonna stop in polynomially many steps.
Yeah.
So, but that's right. That's also a really cool like algorithm, right? It's the simplest one that I know for perfect matching. Yeah. So.
Question.
Oh yeah. Yeah.
Okay. So about the perfect matching, you have a fantastic, combinatorial optimization, much faster with everything a determinist. I mean, you do it as a flow.
No, definitely. I mean, yeah. But if I want to explain max flow to people, I have to define max flow. I have to do a bunch of stuff, right? Like that's what I'm saying. If I pick a person right now, like a random dude in the street, and I say, hey, perfect matching. This is the definition. Here's the algorithm. If I had to explain flow to them and I had to explain scaling, I'm pretty sure scaling will be much better.
No.
right?
But
I think they
when you
wouldn't
have a
listen to you.
problem, you want to solve it.
They probably-
If you have a particular specific problems of optimization, you want to solve it in the most efficient way.
No, sure, and that.
And the most efficient way is this flow for this problem.
Oh, of course, yeah, I'm not, right? It depends if efficient you talk about parallel, in which case this one is the most efficient, right? So, but I don't want to debate on the notions of efficiency here. That was yesterday.
I think,
Yeah.
are you,
Oh yeah, sorry, so again, sorry. The other two open questions, right? We stopped over here on the algebraic solutions because there's all these things to unfold. But then, for example, if we talk about the complexity of these algebraics, what does it involve? Well, we need to kind of figure out what's the complexity of computing invariants. And this is something that also we don't understand very well. Okay, there has been some works on this that kind of have some understanding, but every time we answer one question, it's like a Pandora box. Another question is like, oh, but you have to solve the other question that's the really important one. So we don't understand those questions very well. So can we obtain like more efficient construction of invariants? Because if you remember, if my invariant is simple, like we had in the matrix scaling, this helps us to analyze our algorithm. This tells us that we can stop our algorithms much quicker. But if my invariant is a polynomial that has monstrous coefficients, then like lower bounding the minimum norm is a harder problem. So we get worse algorithms.
usually invariants are not?
Make this any quieter.
That's
One lesson I learned here that there's no chance of evaluating the variance efficiently, usually, but you can still use it for analyzing your numerical algorithms.
right.
Then you don't have to compute it. I mean, evaluate.
Yeah, we never need to. We use them in the analysis.
This
So
works very well.
Even to write them down in very small cases. It's
Yeah, but then you
looks
write
up very
it down and you upper bound it, they're running a
yeah. Because all we need is we need some measure of complexity of the invariant. Even when you cannot compute, just say, oh, your invariance can be generated by something with small coefficients. That's already great for us. It gives us some. And now there's this whole notion of optimization over Riemannian manifolds, right? Can we also get much faster convex optimization in Riemannian manifolds? And we know that certain things, for example, ellipsoid methods kind of won't fly because there's a work of Crisistello and Baumau and also Hamilton and Moitra that says that, those approaches that can't work to give you this log, this exponential convergence. So something in these Riemannian manifolds, the optimization is much harder here. Okay, so getting just improvements on convexity, convex optimization for these manifolds is also really important for us. Okay, and more applications, of course. That's another open question. That's it. Thank you.
Thank you very much. Questions?
I guess the Kampf-Nast function is extremely nice and everything, but all your examples were interesting kind of because the group G you care about is not compact. Are there any interesting applications where you own a compact group, then you have an interesting geodesically convex optimization problem?
Yeah, that's a good question. Maybe.
Yeah, so there's a really simple argument that there's no globally geodesic convex functions on a compact space. So if you're compact, and let's say you're continuous or differential or whatever, if you look at the max, it's also a critical point. But this doesn't preclude, I think, interesting subsets of these cases.
And also, it doesn't preclude the fact that there's not interesting problems with compact groups, right? Because there's a lot of that imaging, the chemistry imaging. I always forget. There's a weird name for it. Do you know the name? Do you
I think
remember?
cryo-EM, right?
Cryo-EM.
I think there's some experts in the audience.
Yeah, so that essentially is is a problem where you have the rotation groups in it, right? They're compact groups, so it's very interesting, and there's different techniques there. I don't know if.
Yeah, because we have some interesting problem on the Grassmann or on the flag manifold, so I was wondering what would be related.
We can talk about it if you're here. Yeah.
I have the impression this can connect you in a way. Well, an idea was to, the general orbit problems for the non-compact group, you can reduce to the compact case. Then one would believe it should become simpler because the group is compact, but it's still very difficult.
Oh yeah, when we talk about the finding the. Yes.
There is a paper on bonus action with my student lab, and hobby is also where we also have some results when the compact group is acting. So maybe I can give you the reference.
Yeah, I could ask one question. Like, when I don't think about optimization around main manifolds, but when we look at like standard complex optimization, there's some distinction between like high accuracy dimension methods like ellipsoid and like low accuracy dimension independent methods like gradient descent. And when you say like better algorithms for convex optimization around manifolds, is it sort of you're looking for like high accuracy methods, like better dependence on epsilon, or?
Yeah, like I would say better dependence on epsilon would be great, because some problems like for us, some problems you need to get exponentially close to the optimum to be able to actually decide the null-con problem.
So you need some like log dependence.
You need log 1 over epsilon dependence. Yeah.
Okay.
Yeah, and there's also like problems with condition number that show up over there because these condition numbers become really large. They can become really large really quickly. So all these problems are there. Like it's much more in its infancy, kind of whatever it is. Like the geometry of like Riemannian manifolds is very well studied, but optimizing over them the way that we want to optimize, like we do in the convex case, it's very new. Like yeah, it's some good progress, but we don't know what we can or cannot do yet.
Questions? Okay, well, let's thank Rafael.